Well, let's start this one a little bit differently. Chances are, unless you're lining the material up in a more non-standard way, that you've gotten to this presentation by first working your way through all the differential calculus of functions of a single variable. And congratulations, that's a solid chunk of work. That's where the approach and the demands that you have seen from algebra, of course, have increased, because in calculus you have to do all the algebra and you have to interpret it and do quite a few things that are much more sophisticated than, say, just simplifying expressions. And now you're starting integral calculus. Well, the beauty as well as frustration with mathematics is that mathematics can and does always go deeper. You can do it for decades and there will still be things that are deeper than the deepest that you have seen before. And so in some ways, going to definite integrals is another one of those jumps. This presentation will be a bit more technical, and because one of the ideas that I have with this material is to try to give you as much immersion as possible right away so that your subconscious can mull it over. This one will take long. You will probably want to take some breaks in between, and I will try to give you some indication where and when you may want to take a break. We will be talking about the definite integral, and that will mean that we'll have to talk about how to set these things up. That's going to be like difference quotients, only more complicated. We will talk about the standard application of the definite integral, which is areas. However, if we were just to talk about areas, then we would be doing ourselves a disservice, because the real key, the real reason why definite integrals are so important throughout mathematics are because definite integrals always talk about what happens when we examine small increments for which natural laws are simpler than they are for the more complicated global situation that we may want to investigate. Let's take a look at what is going on with these small increments. So, well, we know how to compute the areas of rectangles, triangles, circles, and all sorts of other geometric figures. But what do we do with areas with curved boundaries, such as areas under parabolas, like this one here, where, I mean, there is no formula collection that says, okay, here's a formula for this area, or at least there shouldn't be one, because as soon as you turn this quadratic into a cubic or so, you would need a different formula. And that's where the definite integral as a process will help us. And then, of course, this can get even worse, because you could look at areas between curves. Similarly, we know that distance is velocity times time, right? S is equal to v times t. But what do we do when the velocity is not constant over the interval over which we observe the particle that is moving? We know that work is force times distance, W equals F times d. But what do we do when the force is not constant, such as, for example, and this is an image that was made available to me by the Blue Water Tug of War Club, and it's used with the club's permission. Basically, tug of war is a really neat sport, and you may have also played it, not as a competitive sport, but you may have played it in high school sports. Two teams just pull on a rope and try to use enough force to pull the other team across a designated line. And, well, the force that is being applied by these teams certainly is not constant, right? You try to yank, you try to just hold on against people. Sometimes you're being pulled across by the other team, so all of a sudden your force is smaller than the force that the other side applies. And over that whole time interval, you may want to know how much work is being done by these gentlemen here. And of course, that's only one application. Work is something that is very important throughout physics. We also know that the volume of a cylinder is base times height, but what do we do when we've got a non-cylindrical object, such as, for example, a sphere? And of course, for a sphere, there is a volume formula that was known to the ancient Greeks. But where does that formula come from? Well, it comes from the definite integral, actually. It's one of the applications that we will ultimately look at. Here, we're going to just look at a sphere with a given radius, not at a sphere of radius r. And so the thing really is the modeling in this section, in this presentation. That will be a bit challenging, but it really is at the heart of using calculus, and especially integral calculus, in all applications. And the idea is best, the idea of this examining small increments is best explained with an example that actually goes to the standard interpretation of the integral, which is the computation of area. So I want us to compute the area under the function f of x equals x squared from x equals 0 to x equals 2. So let's take a look at this. Well, here's the function, and here's the area. And for the estimations that we're going to do, let's just pretend that this is a piece of oceanfront property that on land at least has straight boundaries, and the ocean here is, I don't know, some kind of a beach, where of course we have a curved boundary. And let's pretend that I'm a realtor who is trying to sell you this property, but of course because you pay for property by the acre, we first have to figure out how large this property actually is. Okay, so me, the realtor, comes in and says, this is what we're going to do. We don't have a formula for the area under this curve. And yes, as a teacher, okay, this is not the realtor, this is the teacher and me saying we don't want to have a specific formula because that would not apply to any other curves, and we want to ultimately have a formula that works for all curves. And so to develop this process, we're going to approximate the area with two rectangles. One rectangle on the interval 0, 1 and the other one on the interval 1, 2. And as the height of the rectangles, we're going to use the value of the function at the right endpoint. So here's the area we want to do. Here's the area we want to compute. Here's the function. We don't know what the exact area is, and now we're going to draw a rectangle here, and we're going to draw another rectangle here. Alright, so the first rectangle, the left endpoint is 0. The right endpoint is 1. The height, as I said, is supposed to be the value of the function at the right endpoint, so that's f of 1 equals 1. And here's the first rectangle. Apologies that the scales aren't equal, but I wanted to have a same size picture. If I make the scales equal, we get a tall and skinny picture. I think you can find those in my book, actually. But other than that, I mean, it's a decent picture of what's going on here. And so the area of this first rectangle is 1 times 1, which is 1. Great. The second rectangle has a left endpoint 1, has a right endpoint 2, has a height f of 2, which is 2 squared, which is 4, which is right here. So the rectangle is this thing, and the area is base times height, 1 times 4 equals 4. Now, ask yourself, if I was a realtor and I told you, this is how I have computed the area of this oceanfront property, are you going to pay me for an area of 4 plus 1, 5 square units, 5 acres or so? Well, hopefully not, because you're paying for stuff that's underwater, right? So something's going on here that isn't quite right. Well, first of all, total area, yes, it's 5. I got that right. Great. So how can we improve this process? Well, we can improve this process if we use narrower rectangles, because that would give us a smaller error. All right, so let's do the same thing again. We use a width of 1/2. And so now the first rectangle has a width 1/2 and a height f of 1/2, so that sits here. Yeah, and f of 1/2 is 1/4. The second rectangle has a width of 1/2 and it sits here, right? And so that would be this one. The third rectangle has a width of 1/2 and a height of f of 1.5 or f of 3/2. And so that would be this rectangle. And the fourth rectangle has a width of 1/2, a height f of 2, like we're seeing here. And that's this rectangle. Okay, now the computation is a little bit harder because, well, 1/2, f of 1/2, 1/2 squared is 1/4, 1/2 times 1, 1/2 times 9/4, and 1/2 times 4. We just square the value of the right endpoint. Then we add that up, and what do we get here? We get 1/8 plus 1/2 plus 9/8 plus 4 over 2 is 2. And now let's see, 1/8 plus 9/8 is 10/8. 10/8 is 5/4, plus 2/4 is 7/4, plus 8/4 is 15/4. Or if we add it up like this, 30 over 8, which is 15 over 4. So we learn a little bit about adding fractions also. But again, here's like Mr. Realtor comes back. I got a better approximation, right? Would you want to pay me for 15/4 of an acre? Or let's see, what would that be? That would be 3 3/4 of an acre. Well, no. Or 3 3/4 acres. Well, no, there's still stuff underwater. Well, one thing that you want to ask yourself, of course, is why do we use rectangles? And that's going to be taken care of by the teacher and me, not the realtor, in the next animation that is going to come up, and that is this process. If we just keep using more and more rectangles, the error will get smaller and smaller, and ultimately in the limit, hey, we're doing calculus, we're doing math, right? In the limit, as we use infinitely many rectangles, we ought to get the right area. Let's see how that works out. So, for more precision, we can do the same thing we did before, only with more data points, and that does get old in a hurry. So, let's assume we evaluate the function at evenly spaced points x0 through xn. And we're going to see the animation actually at the end of the computation. Okay, so how would that look? What would that look like? Well, we would have our interval starting at the left endpoint, which we'll in general call A. And then we have cut points x1, x2, x3, x4, and so on, all the way to xn minus 1. Then we have an nth endpoint, and the nth endpoint is that right endpoint B, where A would be 0 and B would be 2 for us. Our interval has length 2, so that means when we cut it up into n subintervals, right, we've got n pieces that we're cutting it up into, then the individual intervals have length delta x equals 2 over n. So this is 2 over n, this is 2 over n, this is 2 over n, and so on. And the leftmost point should be x0 equals 0. And after that, the endpoints develop as follows. Well, we've got x0 equals 0. x1 is one step over, so that's x0 plus 1 times 2 to the n. x2 is 0 plus 2 times 2 over n. And for this development, you don't want things to simplify. x3 equals 0 plus 3 times 2 over n, and so on. And so the kth endpoint is what you get when you start at 0, and you step k times over, so you have 0 plus k times 2 over n. And that means that the area of each rectangle, which would be this area AK, is f of xk times delta x, which would be xk squared times delta x, which would be 0 plus k times 2 over n squared times 2 over n. And that is something we can plug into a computation now, because the total area, as we use n rectangles now, would be A, approximately sum k equals 1 to n of all the areas A sub k. And we know what the A sub k's are. It's the sum k equals 1 to n f of xk delta x, which is the sum k equals 1 to n xk squared delta x, which is the sum k equals 1 to n 0 plus k times 2 over n quantity squared 2 over n. That's the setup of these Riemann sums, as they're ultimately called. We've done exactly the same thing as we have done with the 2 rectangles and the 4 rectangles, only now we're using n rectangles. Okay, so now we do some algebra, and we realize that as we work out the square, we get a k squared. We get 2 over n quantity squared times 2 over n, which is 2 over n quantity cubed. Then we realize that 2 over n quantity cubed, of course, is not dependent on k, so we can pull that out of the sum. And the sum k equals 1 to nk squared, that is a formula that you may want to look up at this stage, and I will have a theorem ultimately that also says only memorize if people instruct you to do so, and I, for example, wouldn't do that. But the sum k equals 1 to n of k squared is n over 6 plus 2n times 2n plus 1 times n plus 1, so we end up with 8 over n cubed, right? That's 2 over n quantity cubed, times this sum, which is n over 6, n plus 1, 2n plus 1. And this is something we can do algebra with. Now what we want to do is we want to let the width of these rectangles go to 0, which means we need to let the n go to infinity, right? And so let's pair things up in such a way that n's in the numerator are paired with n's in the denominator. So we have an 8, and then one of the n cubes cancels with the n here. That gives us a 1 over 6 for this. The n plus 1 takes another n from here, so we get n plus 1 over n. And the 2n plus 1 takes the third n, so we get 2n plus 1 over n. Now it's really to see that as n goes to infinity, this goes to 8 times 1 over 6 times 1 times 2. 8 times 1 over 6 times 1 times 2, yes. And that's 8/3. And this is now, of course, something that a realtor probably won't tell you, but if we were to do this, you are mathematically educated and I'm your realtor, here's where you would have to really see that, yes, this is the area of this piece of property. It is 8/3 acres, it's 2 2/3 acres, and that's because as we let n go to infinity, the error goes to 0. Now, we ought to see that also, and well, we see it right here because, let's just step back here real quick. The crudest estimate we could do would be just one rectangle, right? Then we could go to 2 rectangles. We did compute that, and we realized that the Riemann sum, the sum of the areas of these rectangles, is of course a whole lot bigger than the actual area. 3 rectangles wasn't something that we computed. 4 rectangles was something we computed. We got the correct number for that, but we can also see that our estimate of 3.75 is a lot bigger than the actual area. But now, as we let n get bigger, we see that the error, which is basically the extra area from these rectangles that sticks out, that extra area gets smaller and smaller, and ultimately we get really, really close to the actual area. And now it repeats, but we can see here that as we let n go to infinity, this Riemann sum, and we'll formally define what Riemann sums are in just a minute, this Riemann sum gets closer and closer to the actual area, and that is the idea behind using definite integrals to compute areas. So, here's the definition. When we've got a function f on an interval ab, then with delta x being just the length of the interval b minus a divided into n little pieces, and xk being the endpoints of these intervals, which is a plus k times delta x, those are the right endpoints, which is a plus k times b minus a over n. The Riemann sum of f over ab within subintervals and evaluation at the right endpoints is, and this notation is individual to me, Riemann sum with right evaluation from a to b, f within rectangles. That's the sum k equals 1 to n f of xk times delta x, which is b minus a over n, that's the delta x here, sum k equals 1 to n f of a plus k times b minus a over n. So that's the setup, and the visualization, which is equally important, is this. Here is our function. We have a, we have b, and now we have our point x0. We want to evaluate at x1, and here's our first rectangle. Here's x2, here's our second rectangle, here's f of x3, and here's our third rectangle, and here, because we only have 4 rectangles, this point is x4, comma, f of x4, and here's our fourth rectangle, and that's what these Riemann sums look like, and of course within it just gets longer and more complicated, as we also have seen in the animation. Okay, so take a function on that interval again, on the interval ab, and with delta x being b minus a over n and xk being the right endpoints, a plus k times delta x, which is a plus k times b minus a over n, we can also define the Riemann sum of f over ab within subintervals and evaluation at the left endpoints, and that would be the left Riemann sum from a to b of f with n rectangles. That's the sum k equals 1 to n. This time we're using f of xk minus 1, which is the point that comes before xk, and if xk is on the right endpoint, then xk minus 1 is on the left endpoint, and that's b minus a over n, sum k equals 1 to n, f of a plus k minus 1, right? If xk has a k here, then xk minus 1 has a k minus 1 here, so a plus k minus 1, b minus a over n. And these things look like this. Here's our function. We have a, we have b, that's the interval. Here's the point x0, comma, f of x0, and here's our first rectangle, evaluation at the left endpoint. Here's the point x1, f of x1, with our rectangle evaluated at the left endpoint. We have the point x2, comma, f of x2, and here's the rectangle that is obtained by using the height, the value at the left endpoint as the height. Here's x3, f of x3, and here's the Riemann rectangle. And here's x4, f of x4, which is not being used because we're now at the end of drawing our rectangles that is similar to the point x0, f of x0 not being used in the Riemann sum as we set up the sums with the right endpoint evaluation. Okay, so the Riemann integral now is the following. A function defined on an interval ab is called Riemann integral if and only if all Riemann sums over ab within subintervals and evaluation at an arbitrary point xk star. You see, there is nothing special about using the left endpoint or the right point. We could use any point in the interval. All those Riemann sums should converge to the same limit as n approaches infinity. So this animation that we have seen for the quadratic, independent of where we put the point where we figure out the height of the rectangle, all these animations, all these Riemann sums should converge to the same value, 8/3 or 2.66666. And if that is the case, then the function is called Riemann integrable. The limit is called the definite integral of the function over the interval from a to b, or the Riemann integral of f over ab. In symbols, with our delta x being b minus a over n, the length of the subintervals, and xk's being the endpoints, a plus k times b minus a over n, we define that the integral from a to b f of x dx is the limit as n goes to infinity, k equals 1 to n f of xk star, where xk star now is not this point. Xk star just says it's a point between xk minus 1 and xk, times delta x, so it's still a rectangle, right? Breadth times height. And that's the limit as n goes to infinity, b minus a over n, because that's what delta x is, times the sum of the f of xk star. And xk star is an arbitrary point in the kth interval xk minus 1 to xk. The function f is usually called the integrand, and the x is called the integration variable. And that is all the terminology at this stage. All right, the visualization is, well, it's exactly these Riemann sums. Let's look at those again. As these Riemann sums, these f of xk star times delta x, those are areas of rectangles. And the more rectangles we use, the better an approximation we get for the area under the curve. Okay, now the important thing to realize is that although the area is a standard interpretation of the definite integral, there are other interpretations, and I want to put that bug in your brain right away. On one hand, yes, areas and integrals are related, but at the same time, there are a lot of other interpretations that will be equally important, and by having those already in mind and letting them marinate, I think we will have an easier time when we get to the more sophisticated applications. So, for any function, the definite integral gives the oriented area under the graph between x equals a and x equals b, and that's because an area, a function can be above the axis or below the axis, and then again here in this picture again above the axis, and as long as the area is above the axis, it's counted positive because our rectangles will have heights f of x k star, and those will be positive heights, right? But if our heights are the values of the function, then when the function dips below the axis, the area will be counted negatively, and that's something that we will have to take into account when we compute overall areas that are not having these oriented properties. And of course, then again here in this picture, when the function is above the axis, the area will be counted positive. Okay, but if f of x is the velocity of an object and x is time, then the definite integral gives the displacement of the object from time a to time b. That's going to be our first application in this section. We're going to talk about that also very carefully, because right after areas, velocities are the next standard application. If f of x is the force that acts on an object at the point x, then the definite integral gives the work that is required to move the object from position x equals a to x equals b. That's the picture that we have seen from the tug of war. That is one of the most sophisticated applications that you see in calculus for the definite integral. We're going to delay that a little bit. If f of x is the cross-sectional area of an object at position or height, actually x, then the definite integral gives the volume of the object between the vertical planes x equals a and x equals b. That is another application we're going to look at. So that's one of the final bugs that I'm putting into your brain in this presentation, that you also want to look at this stuff in 3 dimensions. And basically then really integrals are always about examining small increments. So anytime we are summing small increments, a definite integral may well be lurking in the background. Okay, before we continue, well, we're going to continue a little bit longer here because apparently there's some more on this slide. So because the definite integral gives the oriented area under a graph, quantities that are computed via definite integrals such as work and distance are sometimes visualized as areas themselves. But we want to be careful here, and this is something that confused me as a student. It's just a picture. So work is not area and area is not work. that is just a visualization. We're going to see how that visualization works when we are talking about velocities. And before we go to how the area interpretation can also sometimes help us solve definite integrals, I recommend that you actually take a quick break, because we've thrown a lot of abstract stuff at you. Those Riemann sums do take a little bit to digest. So if you wish, hit pause right now. That's what I'm going to do too, because I need to take a break. My throat is getting a bit dry from the talking. And I will see you for me in a little bit. You may actually want to do some homework problems, and then we're going to keep going and talk about some of the applications. Alright, we ought to be back. My camera ought to be on. Let's take a look at the area interpretation first, because sometimes it can even help us to solve definite integrals. But let me say right away that this following problem or example actually is more of a toy problem. It is something to keep making the connection between areas and definite integrals in your mind. As an application, it isn't that great, because the point of the integral is to use it to compute areas that we can't compute, for which we don't have a formula. If we have an area for which we have a formula, we just use the formula and move on. Let's see what we have here. So we want to find the integral from 0 to 4 of 3 plus square root 16 minus x squared dx. Oh my god. No, we don't want to set up a Riemann sum for that, but if we look at the picture, we realize this is the square root of 16 minus x squared. That's a semicircle of radius 4. And the 3 plus just pushes that semicircle up 3 units along the y-axis. And if we integrate from 0 to 4, then basically we're interested in this area. Well, this area is nothing but a rectangle plus a quarter circle. So we ought to be able to figure out what that area is. And especially after we cut it up into those two pieces that I've just mentioned. Okay, so the rectangle has an area of 4 times 3. The quarter circle has an area of 1/4 times pi r squared, which is 1/4 pi 4 squared. And that means the total area is 12 plus 4 pi. Great. So you will have, probably in homeworks and in books and things like that, you will have some problems like that. And the idea basically is that certain integrals, we could really go back and reduce them to known areas, but the point ultimately really is to use integrals to solve areas, to solve computations that we couldn't solve with formulas. Now, our next application is actually still going in that same direction, because I want to use it as a double check, but that's going to be probably the last time that we're going to look at stuff where the areas are known. So in order to get there, in order to really work with these definite integrals, there are a couple of summation formulas that are useful when we're working with Riemann sums, but please do not memorize these things unless you're instructed otherwise. These frequently used summation formulas are something I can recall in my memory, because I've taught it so often I can't help but remember, but they are not necessarily the heart of everything. So the sum of the first n integers is n halves n plus 1. The sum of the first n squares is n over 6 n plus 1 2 n plus 1. We've seen that already. There's a sum for the first n cubes, which is 1/4 n squared n plus 1 squared. And there's also the geometric sum k equals 0 to nq to the k, which is 1 minus q to the n plus 1 over 1 minus q. These kinds of formulas often are useful when we're working with Riemann sums. Okay, so now here's an application. We want to compute the displacement of a particle with velocity function v of t equals 3 plus 2t from time t equals 2 to time t equals 5. Now that looks like it's totally different than area computation, and yet in principle it's very similar, because we know that distance is velocity times time, s equals v times t, and the problem is the same as what we had for the area. The velocity is not constant over the interval, and that's the same as when the upper boundary of the area is not straight. So we cut up the interval and we set up a Riemann sum. Basically, The left endpoint of the interval is a equals 2. The length of the subintervals delta t, not delta x, because we're looking at time here, of course. Delta t would be b minus a over n, which is 5 minus 2 over n, which is 3 over n, no problem there. The right endpoints of the subintervals tk are a plus k times b minus a over n, which is a plus k times 3 over n. And so now the distance, well, the distance is the limit as n goes to infinity of the sum k equals 1 to n v of tk delta t. Okay, so here's where we have to think a bit. Basically what I'm doing is I'm cutting the interval into short intervals that have a very short length delta t. Now, independent of the fact that our velocity function is not constant, if the interval is really, really short, then the velocity can't vary much over that interval, and that means that the velocity can be said to be approximately v of tk. It can be approximately the value at the right endpoint. And so that means that v of tk delta t tells you roughly how far the particle travels throughout the kth time interval. And if I add that all up, I get the total travel distance. So this apparently has a chance to work. It does work. And now we just have to set it up. And that's now just setting up Riemann sums, right? Sum k equals 1 to n stays with us. V of tk would be 3 plus 2 times tk, 2 times 2 plus k times 3 over n, which is right here, times the delta t, which is 3 over n. And from here on out, make a pause in your mind. We have set up the Riemann sum. This is the important part. This is the application. This is the examining small increments part that I'm going to keep hitting you with, because that is really the important part of what we're doing here. The rest is computation. Now, computation is not unimportant either, because we've got to get it right. And it is good practice of working with summations and with limits and all sorts of other things. But the creativity, the things that ultimately a computer can't do, the things that you have to do and then fit into a computer, that's the stuff that is happening right up front here. But now, well, let's simplify. So, well, yeah, 3 plus 2 times 2 is 7. 2 times 3 times k times 3 over n is coming from the 2 times the k times 3 over n. We still have the 3 over n here, and I think now we're going to separate out the sums. Well, we multiply out the parentheses. 7 times 3 over n. 2k times 3 over n times 3 over n is 2k 3 over n quantity squared. Now we can split up the sums here, and we probably can also take out the 3 over n's already. Yeah, basically, 7 times 3 over n, we can take the whole thing out. 7 times 3 over n, and what remains inside the sum is 1, right? If you factor 7 times 3 over n out of itself, you keep a 1 on the inside of the, basically the sums are parentheses, so you keep a 1 on the inside. And for the other one, well, we break up the sum of the whole thing is the sum of this one plus the sum of that one. And then the 2 and the 3n squared don't depend on k, so we can pull that out. 2 times 3 over n quantity squared times the sum k equals 1 to n k. Alright, now we have to compute the sums. This one you don't need a formula for. If you add 1 to itself n times, what are you going to get? You're going to get n, right? And this part here is 7 times 3, so 21 over n. The other one is a bit uglier. Well, 2 times 3 over n squared. 3 squared is 9 times 2 is 18. The denominator gives us an n squared. And the sum of the first n integers is n halves n plus 1. That was something we had before. Now we simplify a bit. Well, n over n goes away, gives us just a 21. And then here n over n squared, that gives us a 1 over n, and the 1 over n is being paired with the n plus 1. So we get 18 times 1 half times n plus 1 over n from coupling the n plus 1 with the n that is left from the n squared. And as n goes to infinity, that ought to be going to 21 plus 9, which is 30, because 18 halves is 9. Yeah, okay. So that's the computation there. Let's do a double check, and this is this visualization via areas that you will also see in physics, and where you just have to be careful to realize that no, we have computed the distance, we have not computed an area. But if we plot velocity over time, then because we know that distance is velocity times time, then the displacement really is, or can be visualized as, the area underneath the curve. And so what do we get here? Well, we have an area that consists of a rectangle down here and a triangle up here. The rectangle has width 3 and its height is 7 here, because that's about 7. You can also work that out from the fact that f of 2 is 7. And 3 times 7 is 21. And the triangle has width 3, and it has height 6, because f of 5 is 13. And so then we have that the area of the triangle is 1/2 times 3 times 6, which is 9. And so the total area is 21 plus 9, which is 30. All right, so what else can we do? Here is where the visualization gets more sophisticated. So if you want to, give yourself another break right here. I'm going to continue, but putting into your mind the idea that displacements can also be computed with Riemann sums, and the setup of a more complicated Riemann sum that doesn't start at 0, that's the next stage. Now, let's take a look at how we compute the volume of a sphere of radius 2. Ha! I already clicked on my animation. Basically, the idea is that a sphere has round cross sections, right? It's got cylindrical cross sections. And if we cut that sphere up into little cylinders, if we make the heights of these cylinders smaller and smaller, if we slice this sphere into really, really tiny slices, then the total volume of these slices, even though the individual slices, as we can still see here, even though these individual slices are definitely cylinders, something for which we can compute the volume fairly easily, we can see that if we make these cylinders sufficiently thin, then the total volume of these cylinders ought to be really close to the volume of the sphere. So this is just the three-dimensional analog of what we did with the Riemann sums for areas, where we approximated areas with rectangles. Now we're approximating three-dimensional volumes with cylinders. Okay, the setup therefore is really a very widely applicable principle. That is why I want to introduce it right away. That is why I'm going to keep bothering you with it, because I want you to start also trying to visualize in 3D. That is not something that comes easily. I have seen students, when they made the transition from single variable calculus to multivariable calculus, have difficulty with popping that extra dimension into their visualization, even though their 2D stuff was great. So let's push our mind also in that direction. The setup is, well, it's approximating the volumes with the cylinders. Yeah, sure. We just did that. Oh yeah, that was just pushing things away. Here is the cross section. So our sphere, if we're taking a vertical cross section, well, the vertical cross section is just a circle. I'm going to approximate that sphere with little slices. And of course, in some ways, it sounds like we're adding insult to injury, because I keep talking about 3D. First thing that I'm doing as I'm visualizing is I'm cutting the third dimension out. I'm basically saying, look, we know that if we rotate this around the y-axis, we get something that looks like a sphere, and these things look like cylinders. But that's actually a standard approach, and it's also part of this widely applicable principle. When you want to visualize three-dimensional objects, you visualize cross-sections. Now, these cross-sections all have, these little cylinders here have all height delta h. All the way through, every one of them has the same height. And delta h, therefore, is the end point, 2, minus the starting point, -2, divided by n, the number of cylinders. And that's 4 over n. So we have delta h equals 4 over n if we set this up with n cylinders. The cylinders start at y0, y1, y2, y3, and so on, all the way through yn minus 1, yn minus 2, yn minus 1, and yn. So that's y0, y1. It's the lines that we have here. And how do we get those? Well, yk would be that you start at -2, and you step up k times delta h, which is -2 plus k times 4 over n. So that's what these yks are. Now let's take a look at the volume of the kth slice. So let's take one of those slices here, and let's just say it is at height y. Well, then we know that the height of the slice itself is delta h. We know that the radius of the slice, because this thing here, here's another one of those pop quiz things. What's the equation of a circle of radius 2? Well, it's x squared plus y squared equals 4, which means that this x, which is the radius, right, we're going in the x direction here, the radius would be square root 4 minus y squared. And that means that the area of the base here is pi times the radius squared, pi times 4 minus y squared. And that gives us that this volume delta V of this little slice here, sorry about the double vision by the way, the volume of this little slice here is just pi times the radius at height y squared times delta h. I'm saying approximately because we're losing a little bit here, just like with higher slices we would gain a little bit, but the delta V in the sphere is approximately that. And we can write that out. That's pi times square root 4 minus y squared quantity squared times delta h, which is pi times 4 minus y squared times delta h. And this is now something that we can do the computation with. The volume is approximately the sum k equals 0 to n minus 1 delta vk, which is the sum k equals 0 to n minus 1 a of yk delta h. Okay, why do I start at 0? Because I used the bottom, the y at the bottom to compute the radius, so technically we've got a left endpoint approximation here, but we know left endpoint or right endpoint approximations really will in the limit always give us the same thing, namely the actual value. Now we plug things in. This is the sum k equals 0 to n minus 1 pi times 4 minus yk squared delta h, which is the sum k equals 0 to n minus 1 pi times 4 minus, and the yks were negative 2 plus k times 4 over n quantity squared. So the only thing that happened here is that we replaced the yk. It highlights the yk squared. Okay. Well, we replaced the yk and we replaced the delta h, which is with its value 4 over n. Okay, knowing myself correctly, the next thing we do is we multiply out the parentheses. And yes, that's exactly what we're doing. So what do we get? We get negative 2 squared. Well, so we get 4, but we get it with a negative sign. 4 minus 4, that just goes away. Then we have 2 times negative 2 times k times 4 over n. Well, so that would be negative 16k over n. And with the extra negative sign, we get plus 16k over n. And then the last one here is plus 16k squared over n squared, and the negative sign up front gives us the minus here. And you notice that I didn't really concentrate on much else, and that's because everything else we've just kept. Okay, so we work that out. Well, 16 times 4 is 64. N times n is n squared, so the first sum has a 64n squared k. And, well, pi is in common, so we factor out pi. The first sum has a 64 over n squared, which we factor out. We keep a sum k equals 0 to n minus 1k, which is this k. The second sum has a 64 over n cubed k squared. And we factor that out, and we keep the k squared. This k squared here is this k squared here. Now we can apply those formulas where, hey, if your teacher wants you to know them, you just have to memorize them, but I would just look them up here, and we get that this is pi times 64 over n squared. We're summing to n minus 1, so the n halves n plus 1 ends up being n minus 1 halves n minus 1 plus 1. The 64 over n cubed we keep. The n over 6 is n minus 1 over 6, because we only go to n minus 1. The n plus 1 is n minus 1 plus 1, so that's n. And the 2 quantity n minus 1 plus 1, that's just a 2n minus 1. And now in order to compute a limit, again, we do some cancellations. And, well, n squared and n cancel each other. And then we might as well take the remaining n and put it under the n minus 1. Here we have an n that cancels with an n from the n cubed, so we keep an n squared, and the n squared can be broken up into an n that goes here and an n that goes here. And other than that, we kept everything else. And now if we take the limit of that, that would be pi times 64 over 2 minus 64 times 1/6 times 2. And that's exactly what we have there. Pi times 64 times 1/2 minus 64 times 1/6 times 2. Let's see if we can figure out what that is. Well, 64 over 2 is 32, of course, so we get 32 plus, and here we have, not minus, okay, so 32 minus 64, minus 32 over 6, so that would be 5 times, come on, 32 minus 64 over 3. Yeah, okay, so that's actually better worked as 64 over 2 minus 64 over 3, which is 64 over 6, which is 32 over 3. 64 over 6, and of course we have the pi from out front. 32 over 3 times pi. And that is actually correct, hang on with that, because if we work out the volume of a sphere of radius 2, that's 4/3 pi r cubed. Well, 4/3 times pi times 2 cubed is 4/3 times pi times 8, and 4/3 times pi times 8 is 32/3 pi. The thing here is, however, that with integrals we can actually prove that the volume formula for a sphere is correct, and at some point in time you may even be doing this on homework or in the book. Okay, there are other things we can do because sometimes we may not have enough data available. So we can also use this idea of Riemann sums for estimation. So here's another point where if you've got a headache by now, if this is really rough, and I wouldn't blame you for that, take another break. If we have sparse data given, so for example, if somebody has measured the velocity of an accelerating car every half second, and so we've got the velocity at times t equals 0.51, 1.5, and 2. If we want to compute the distance that the car travels from time t equals 0 seconds to time equals 2 seconds, well, there really isn't that much we can do. We can say from time t equals 0 seconds to time t equals a half second, we had a velocity of 0 meters per second times a half second gives us 0 meters. From time t equals a half second to 1 second, we had a velocity of 0.25 meters per second times a half second gives us 0.125 meters as a distance traveled. From 1 second to 1.5 seconds, our velocity was 1 meter per second times a half second gives us a half meter traveled. And from time t equals 1.5 seconds to time t equals 2 seconds, our velocity was 2.25 meters per second. And we end up with, 2.25 meters per second times a half second, which is 1.125 meters. And if we add it all up, we get 0 meters plus 0.125 meters plus 0.5 meters plus 1.125 meters, which is 1.125 plus 0.125 is 1.25 plus 0.5 is 1.75 meters as an estimate. And you might be saying here, yeah, right. I mean, do we really believe that the car stood still for the first half second and then all of a sudden it moved at a velocity of 1/4 meter per second? That's not right. So, well, the estimate is not the actual value. What can we do? Well, we can do it again. Okay, if we do it again, we could also say that from time t equals 0 seconds to time t equals a half second, the velocity was 0.25 meters per second times a half second is 0.125 meters. From a half second to 1 second, our velocity was 1 meter per second times a half second gives us a distance of a half meter. From time t equals 1 second to time t equals 1.5 seconds, our velocity was 2.25 meters per second times a half second gives us 1.125 meters. And from time t equals 1.5 seconds to time t equals 2 seconds, our velocity was 4 meters per second times a half second gives us a displacement of 2 meters. If we add that up, 0.125 meters plus 0.5 meters plus 1.125 meters plus 2 meters, 1.125 plus 0.125 is 1.25, plus 0.5 is 1.75, plus 2 is 3.75 meters. And you can say the same yeah, right over again, because we also don't necessarily believe that the car immediately moved at a velocity of 0.25 meters per second. What else can we do? Well, unfortunately, nothing much. As long as, or assuming that the velocity increased steadily so that we didn't have anything where the car was going at 1 meter per second, somewhere in between here, and then decelerated back down to 1/4 meter per second. Assuming that the velocity increased steadily, we can say that the car moved at least 1.75 meters and at most 3.75 meters, and that's an estimate. When sparse data is all we have, then there is really not much else we can do. Okay, we could also take the average of the estimates, which would be 2.75 meters, and that presumably is closer to the actual data, but that's it. Now, if we had a function, we could set up finer Riemann sums, but without more information, this really is it. The finer Riemann sums, by the way, would be very similar to one of our first examples, because this is sample data from the function f of t equals t squared. But we don't know if this sample data really is coming from that function or a function that just happens to go through the very same points. So if somebody gives you sparse data, that's just about it. We're coming therefore now to the, well, this promises to be abstract because it's theorems, but actually this is something that is nice and visual, and usually as you do these homework problems, these problems are a bit of a relief because they're not that hard. So let's take a look at them. If we've got a continuous function on an interval AB, then the function is also integral over the interval AB, and that just says that any decent function that we've been working with so far we can compute the integral of. A function is piecewise continuous if we can piece it together from functions that are continuous. So as long as you can cut up your interval into subintervals on which the function is continuous, we ultimately for integrals also don't have a problem, because piecewise continuous functions on an interval can also be integrated. And now, if you've got two continuous functions and c is a real number, then the integral of a constant multiple of the function is just the constant multiple times the integral of the function. That makes sense, right? Because the integral ultimately is a sum. And if you multiply every summand by c, that's the same as when you multiply the whole sum by c. The integral of f of x plus g of x is the same as the integral of f plus the integral of g. That also makes sense because remember the integral is a sum. And if I sum a bunch of small sums, then that's the same as if I first sum all the first terms and then sum all the second terms. The integral from a to b f of x dx is negative the integral from b to a f of x dx. Well, if we go left to right, our integrals, our little distance, the widths of our rectangles are positive. However, if we go right to left, well, then b minus a would be negative, so our little lengths of intervals, our little dx's, are negative, and then this extra negative makes them positive again, and we get the same integral that way. And, well, if we've got continuous functions and there is a point in between, then we can cut up the integral. So the integral from a to b f of x dx is the integral from a to some point in the middle, f of x dx, plus the integral that continues from that point in the middle to b. And that is something that is visual, because if we have our function here, here's a, here's b, right? Here's our point in the middle, that's where the integral cuts up. Well, then the integral from a to m f of x dx is this area. The integral from m to b is this area. And of course, if you add those areas up, you get the total area under the function. This leads then to examples that just are supposed to get us used to piecing integrals together. So if you've got two continuous functions on the interval from 1 to 5, so that we've got the following. The integral of f from 1 to 5 is 3. The integral of g from 1 to 4 is 7. The integral of g from 4 to 5 is negative 4. Well, if we then want to compute the integral from 1 to 5, 3f of x 2g of x dx, well, we take the integral from 1 to 5, 3f of x plus 2g of x, and that is 3 times the integral from 1 to 5 f of x dx, plus 2 times the integral from 1 to 5 g of x dx. Well, we've got the integral for f, we don't have the integral for g, so we piece that together as we're just copying it down here, 3 times integral from 1 to 5 f of x dx plus 2 times, and this integral breaks up into the integral from 1 to 4 plus the integral from 4 to 5. And now we just plug in the numbers, right? 3 times this integral, 3 times 3, plus 2 times the first integral is 7, plus the second integral, which is negative 4. And that ends up being 9 plus 6, that ought to be 15. That's correct, and that's it. So even though that feels abstract, it's also actually fairly quick, right? Sometimes we can also look at even and odd functions, and there are a few tricks there. So let a be greater than 0, let f be integrable. If f is an even function, then the integral from 0 to a of f of x is the same as the integral from negative a to 0 of f of x dx. And if f is an odd function, then the integral from 0 to a f of x dx is minus the integral from negative a to 0 f of x dx. Why is that? Well, if you have a function that somehow traps area, here's area AR, BR, and CR, so subscript R for right. If this function is even, we know the even function is symmetric across the origin, which means the area AR will have a counterpart AL, which has the same size, it's only on the left side. The area BR has a counterpart BL, same size, only on the left side. And the area CR has a counterpart CL, same size, only on the left side. Which means the integral from 0 to some point on the right of f of x dx that is made up of AR, BR, and CR would be the same as the area from negative a to a f of x dx, which is made up of CL, BL, and AL. Similarly, for odd functions, well, for an odd function, let's just say we've got an area here. But an odd function is rotationally symmetric around the origin, so it continues like this. This area here looks like this area here, but this area is positive and this area is negative, which means when you go from 0 to a f of x dx for an odd function, if you go from negative a to 0, you get the same size, but you get the opposite sign because the area has been rotated underneath the axis. Okay, so we're already at the conclusion, and hallelujah for that, because this was a very long presentation. The modeling process of considering little increments that connects simple formulas S equals V times T, area equals base times height, volume equals base times height, and so on. That modeling process, which takes these little increments and connects the simple formulas to more complicated real situations, such as varying velocities, areas with curved boundaries, complicated volumes. So that's considering little increments just connects these simple formulas to the more complicated real situations. And that is the heart of definite integration, even though that ultimately is something that is the hardest part. That is why we're doing definite integrals, and we're going to see that in separate sections again. We're going to talk about areas a lot. We're going to keep coming back to velocities. We will have a separate section on volumes. We will have a separate section on work. So this is something that we're going to hit over and over again, but keep that idea in mind. That is the heart of definite integration. That is what you're going to see of definite integration in physics, for example. The visualization and modeling can become near arbitrarily complicated, but that's exactly why we do calculus. At this stage, as we consider real-life situations, the beauty is not that the computation is quick and simple. The beauty is that the computation is possible. It's important to structure your thinking there. So the modeling cannot be simplified because it depends on the situation. For example, I can't present a simpler hydrogen atom when discussing certain differential equations because the hydrogen atom is as it is. But as you structure yourself, as you realize that you always cut things up, once you cut things up, you figure out what's going on with these little pieces, the little displacements, the little areas, the little volumes, the little delta of work that we're going to have. And if you realize that once you've got your Riemann sum set up, the rest is computation, which is also complicated, but which is a separate issue. As long as you have that structure, and as long as you're on top of those pieces, these computations will work just fine. Certain computations can be abbreviated. We will soon see in the fundamental theorem of calculus, and that we can shortcut the limit computations that we've done here. And of course, we're going to use the fundamental theorem of calculus to really do that shortcut. The limit computations and the Riemann sums are very similar to the difference quotients that we had for differential calculus, which we also ultimately abandoned in favor of faster computations. So in practice, however, then a lot of computations are done numerically. And as you set things up numerically, you're exactly back to where we started. You're examining little increments, and you're setting up what amounts to Riemann sums or more sophisticated cousins of Riemann sums. So do not take those Riemann sums lightly. However, so the last thing then is there really is a certain correlation between being able to compute really nasty stuff and being able to work with models. And my conjecture is that this has something to do with being able to concentrate on a task. And of course, if you can mess with an ugly Riemann sum, that trains a lot of concentration ability. So overall, even though this stuff is challenging, I want you to face that challenge head on. Now, the first challenge you might have is to cure the headache that you have right now. You may be tired. I don't blame you for that. I intentionally threw a lot of stuff at you right away, and that is because you have a lot of the ideas and all the computations for Riemann sums in this presentations. We've sown a multitude of seeds that now can germinate in your mind, and as we get back to Riemann sums, as we get back to definite integrals computing areas, as we get back to computing volumes, as we get back to computing distances, as we get back to volumes, or to work, and so on and so on. As we keep revisiting this area of examining small increments, this stuff that right now looks really, really hard is going to come back to us. We're going to see it. It's going to look more and more familiar. Some of the stuff that didn't make sense here will start making more and more sense, so that when we are done with all the modeling for integrals, you ought to be able to have overcome this challenge here, and you ought to be able to set up these sums and then solve them either with integrals or numerically. But until then, you have earned a break. Hey, I've earned a break. I'm a little bit dizzy because I've been talking a lot. So let's stop this thing, and I'll see you in another presentation a little bit later at your choice.